Okay, so we've talked about three different methods for solving systems of linear equations. We've talked about graphing, we've talked about substitution, we've talked about elimination. In all of these cases so far, we've been able to find the point of intersection of two lines, which is represented by an ordered pair. Using GeoGebra here, we have two lines, a blue line and a red line, and this green point A is their point of intersection. The coordinates of this point, which are 1, 1, will satisfy the equation of both the blue line and the red line, making that the solution to the system of equations. What we're going to talk about right now is some special cases, because two lines don't always intersect perfectly at just one point, and that's what we're going to look at today. In this first special case, number 1, we actually are going to have no solution. As opposed to being able to find an ordered pair, x and y, that satisfy both equations, we won't be able to find a single ordered pair that satisfies both. That means that there's no solution. Graphically, this is going to look like two parallel lines. These lines, which extend forever and never touch, will have no shared point of intersection. So anytime you see a graph of two parallel lines, which is sometimes indicated by triangles or arrows on the lines, you'll know that there is no solution to this system of equations. Now, what would this look like algebraically? Well, if I take my equations over here, 3x plus 4y equals 7 and 6x plus 8y equals negative 4, and I want to solve this system, I can use either elimination or substitution if I don't have a graph or I want to use some other method just to see what happens. In this case, I'm probably going to choose elimination because none of my variables are particularly easy to isolate. And also I noticed that I can really easily eliminate the x's because they're not, the like terms here are really easy to get to be exactly the same. All I have to do is multiply my first equation by 2. And when I multiply the first equation by 2, that becomes 6x plus 8y equals 14. And just to bring the other equation down below it, that's going to be 6x plus 8y equals negative 4. Now, this is not necessarily something that I would have expected, but I actually have created a situation where both my x's and my y's are like terms that are identical. So because they're the same, I'm going to go to subtract it, and by design, 6x minus 6x will cancel out. And then, as I mentioned, kind of this unexpected occurrence, 8y minus 8y also cancels out. Now, I can't just leave it blank on that side of the equal sign, so I'll put in a 0 to keep that over there. On the right side of the equal sign, I get 14 minus negative 4. Now, minus a negative is a plus, and so 14 plus 4 is 18. Well, I've got nothing left in this equation here. This is no more x, no more y. I'm left with a statement 0 equals 18, but that statement is just plain false. It's not solvable. There's no possible time that 0 ever equals 18. So anytime you're solving algebraically using either elimination or substitution and you get a statement that's false, one number equals a totally different number, you can conclude that there is no solution to the system. There's no single point that can be written as coordinates xy that is on both this line and this line because the lines are parallel. And so that's the conclusion that you can draw anytime you get a false statement. When the lines are parallel, they do not touch, and there will be no solution to the system. Our second special case is when we have infinitely many solutions. As opposed to just having one ordered pair, we're not going to be able to choose which one we want because two lines are going to intersect all over the place. You can tell here that actually there are two lines drawn, a red line and a thick blue line. The thickness is just there so you can see that the two lines actually occupy the same space. One line is drawn over the other. And I actually have their graphs here. One's in standard form, one's in slope-intercept form. And so we can see what's going to happen is these actually are going to be the same equations, just written differently. That's what makes these two lines the same. So if graphically you ever see two lines on the same coordinate grid that are exactly the same, and you're asked to solve the system, you can immediately conclude that there are infinitely many solutions. That means that this point's a solution, this point's a solution, this point's a solution, this point, any point on these lines is on both lines. So it has an infinite number of solutions. What does this look like algebraically? Well, if I have my two equations over here, I can try to solve the system of equations using one of my other two methods, if I don't want to use the graphing method. So maybe I'll try using substitution, since I already have the y by itself. So since the y is by itself here, I'm going to plug in for this y using this expression. That's going to look like this. I'm going to have 3x plus 4 times, now I'm going to plug in all of my other expression for y. Negative 3/4 x plus 7/4, and then complete the equation that I had before, which was equals 7. Seems like a bit of a pain because I have fractions, but the distributive property here is actually going to take care of it pretty nicely for me. It might be beneficial to treat that as a 4/1, just to remind myself when I multiply fractions to multiply the numerators and multiply the denominators. My 3x will come down exactly the same. Then when I do 4 times negative 3/4 x, that's going to become minus 12/4 x. Same thing over here with the 4 times 7/4. That's going to become plus 28/4 equals 7. Now those fractions are fairly convenient because they reduce. 12/4 x is 3x. 28/4 is 7. Now, you could have actually jumped right to this minus 3 and the 7 based on this minus 3 and this 7 because my 4 as my numerator was multiplying two fractions that had 4 as a denominator. So it actually would cancel out in each case there. But if not, this method will still get you to the answer that you need, which is right here. Now I just combine the like terms, and 3x minus 3x cancels out, leaving a 0, and 0 plus 7 is 7. So I get 7 equals 7. Just like in the last special case, I no longer have a variable. And I have an equation. Last time it was 0 equals negative 19. Here it's 7 equals 7, which is actually always true. It doesn't matter what x is here or what y is here. It means that 7 is always going to equal 7. So no matter what, I have a true statement. If you're solving using either substitution or elimination, and you come to a true statement without variables, you can conclude that you have infinitely many solutions. Now, one thing I want to make a quick note of is this does not mean all real numbers. First of all, our answers aren't just numbers, they're ordered pairs. But other points that are not on either line, such as 3, 2, that's not a solution to the system. It's not a solution to either line. Only the points on the line are solutions to the systems. Now, there are still an infinite number of them, and to find any one of them, all you would have to do is pick a value for, say, x, plug into your equation, either equation, since they're both identical, and you'd get one of the solutions could be, for example, 1, 1. That would solve both of these equations and therefore be one of the infinite number of solutions to this system of equations. This is our second special case when the lines are the same. The system of equations has an infinite number of solutions. One thing we can talk about with these special cases is how the equations of the lines are connected. Well, we know from our last chapter that if two lines have the same slope, they may be parallel. If we can write the equations of both lines in slope-intercept form, we can quickly tell whether or not we have a special case. In this first example here, I have y equals 3x plus 6 and y equals 3x minus 4. In both cases there, I find that m equals 3, using y equals mx plus b, which is my slope-intercept form. Now, because they both have the same slope, we think that they might be parallel, and they're actually definitely parallel because their y-intercepts are different. that means that they're not exactly the same line, but they are parallel. If these lines are parallel, that means they're going to have no solution when we think of them as a system of equations. If I look at these two equations over here, y equals 4x minus 5 and y equals 4x minus 5, well, certainly, just like before, their slopes are identical. They're both 4, using y equals mx plus b. But in this case, their y-intercepts are identical as well. These are actually the same line. It's just a repeated line. And when that happens, it's our second special case. That means we have infinitely many solutions. Remember, this is not the same thing as having all real numbers or all real ordered pairs as our solution. It just means that there are an infinite number of solutions. We can't possibly list them all. Looking at this third example, y equals 2x minus 8 and y equals 7x minus 5, these slopes are not the same. Immediately from that, I know that I'm just going to have one solution, which is really kind of convenient. I don't care what the solution is to this particular problem. If I'm asked to find it, I know that I can use substitution or elimination to do so, but I do know that I will just get one solution. It's not a special case. This just means the lines intersect. Maybe they're perpendicular, maybe they're not. That doesn't make a difference. All that matters is they intersect at one point. And so that's how you can use slope to determine if it's a special case, and if so, which special case we have. All right, just need to wrap up everything we talked about here. The systems of linear equations can have three types of solutions. Either one solution, where the lines just intersect like normal, maybe perpendicular, maybe not, doesn't matter. They could have no solution, where the two lines are parallel. They actually could have infinitely many solutions if the lines are exactly the same. Remember that algebraically, if we use elimination or substitution, the one solution problems, we'll be able to find a value for x and y. Could be 0 in one or both cases, but we can get actual numbers for x or y. For the no solution, when we're solving using one of those two methods, we'll end up getting a statement that's false, something like 2 equals 4. That tells us that we have no solution. The lines are parallel. If they have an infinite number of solutions, algebraically that's going to look like an equation that is true, always true, something like 3 equals 3. Variables disappear and we're left with a true statement. We have an infinite number of solutions because the lines are actually the same. Just for some vocabulary, a system of equations that has one solution is called consistent independent, as opposed to a system that has an infinite number of solutions, which is called consistent dependent. The reason for this is consistent just means that there's going to be a solution. Dependent means you have to figure out which one you're talking about. It depends on where your x is to find what your y is. Your independent solution is the only one solution where those two lines meet. If the system doesn't have a solution, then it's called inconsistent. And that summarizes the special cases for systems of linear equations.